10 years ago, I was about 2 years after my master's, and I didn't work in mathematics. I worked in education, and 4 days a week, out of the week, because one day of the week I decided that I want to still learn about mathematics. And I came here as an auditor, as a שומע חופשי, to Alex's course. And you can argue that it changed my life, because like learning about the congruent subgroup problem, property and profinite groups, and kind of reinvigorated me. And I chose to actually start my PhD, and specifically being mentored by Alex. It's funny that you said, because also my Ido Efrat, my master's advisor, said the same thing. So it seems to be everyone agrees that education is more important. Nevertheless, I chose to come back to mathematics. And here I am. So thank you, Alex, for the mentorship and all the years and the math that we did together and everything else. Thank you. Okay, so I'm talking about Connes embedding problem. I'll maybe discuss some things that are also related to work that I've done with Alex and some colleagues of us, but I'm actually I want more to focus on the work. So this is Connes embedding problem and quantum information theory. Okay, let's do a shorter version of the title. And I'll mainly cover kind of the reduction of Connes embedding problem to a problem actually in quantum information theory called Cyril-Son problem. Cyril-Son's problem. That's essentially what I will do today. And I hope I'll give all the correct references along the way, but please, if Alain Connes is in the audience, please correct me. And the second part will be to cover the work of G, Natarajan, Vidick, Wright and Yuen. Natarajan, Vidick, Wright, and Yuen, who showed that, who solved Cyril-Son problem, solved TP, let's call it, by proving a computational complexity result, which says that a certain complexity class, so this is defined even like with some time constraints on the computations allowed in this model, and it's okay that you don't parse what I'm saying now, but anyway, this computational this complexity class is as hard as the halting problem. Okay, that's what's written here, and I'll discuss this tomorrow. So you don't need to know anything about what's written here. I'll explain everything tomorrow. Today we're only focusing on this part. Okay, great. And the plan is to, at least for today, so plan for part 1 is to first give some motivation. Motivation to what? To some variant of the Connes embedding problem. The second part will talk about characters. And the third part will talk about non-local games. So I'll have a 3-part talk today, and let's start from the motivation. So we all know that when you have a polynomial f in one variable over some field, maybe this polynomial doesn't have any roots in this field, but at least if the degree of the polynomial is not 0, you can deduce that there exists an extension field containing f, and there is an element alpha in this extension such that f of alpha is 0. So that's basis Galois theory 101. And there's a famous question, what is the correct group analog of this? So let me try to phrase to you what would be a reasonable group theoretic analog of this. So what would be the analog of a polynomial? It would be a single variable word. So gamma is a group for me. What would be a word with a single variable with coefficients in this group? It's something of the following form. An element of the group, the variable to some power, which is an element of z, like an integer, an element of the group, some other power of x, etc. x e n gamma n. Okay, so the ei's are in Z, and the gamma i's are in the group gamma. So it's the free product of gamma with Z, right? That's what happens here, and X is the generator of Z. And what would be like a candidate of this? You want to say that there exists some gamma prime containing gamma and some alpha in gamma prime, such that W of alpha is equal to the identity element. That would be the analog of this Galois theoretic problem. But what is the analog of the degree? Okay, what does it mean to be degree non-zero? You can be naive and just ask for some power of x to appear somewhere, but it turns out that this is not enough. So let me give you an example. If you have some group which has finite order elements, you can take the following word, ax, bx inverse. Okay, that would be wx. And notice that if this is 1, it means that A and B are conjugate. So if you choose your two elements to have different orders in your group, so if the order of A is not the same as the order of B, you cannot solve it no matter in which extension you take, because they will never be conjugate. You're going to force somehow their order to change by embedding the group in a bigger group. So what would be the analog of the degree? Notice that the sum of exponentials here is 0. So the correct analog of degree non-zero is just that the sum of exponential is non-zero, and this is called the Kerver-Laudenbach conjecture. Kerver-Laudenbach conjecture. It's from the, okay, it's hard for me, I didn't find the actual reference to this. It's kind of, you know, someone referenced someone, that this is called the Kerver-Laudenbach conjecture. It for sure was known in the 30s, probably was known even before. Writing 30s without having the correct reference in hand. So what is the conjecture? If the sum of the exponents in the word, so the sum of ei's is not 0, then there exists a gamma prime that contains gamma and an element in gamma prime such that W of alpha is the identity. Okay. Now, why do I even mention this conjecture?
You have you take the free product and you mod out by W. What do you get?
Yeah, the question is, does gamma embed in this group? That's equivalent, right? So you will notice that many of the problems that I'm going to discuss can be rephrased as embeddability problems, and you're right. This can be phrased as some embeddability problem of gamma in the free product of gamma with Z mod the relation induced by W, right? That's like what happens here. Okay, great. So this is still open. I will just say there are interesting cases that are known. Actually, like Tzachik is not here, but like Tzachik gave a sadna at the Hebrew University when he was a professor here and also in Weizmann, and he has this famous problem of ants going over like a polygon. You know this on a polytope in three-dimensional space. You know this problem with ants on every for every face of a polytope, of three-dimensional polytope, you put an ant on one of its edges, and they walk around, and there is just some lower bound on the speed which they are allowed to walk, okay? And they just go around clockwise around their face, okay? That's what they're doing. The claim is that they will bump into each other at some point. And it turns out that this almost riddle that you can ask, I don't know, like a bright teenager.
You can ask anyone.
You can ask anyone. Yeah, right, okay, yeah. You can ask anyone. So this question turns out, if you solve it, you can solve this problem when the sum is equal to 1. So it turns out that the answer is yes when this sum of exponents is 1, and you use this lemma somewhere, this property of ants walking on polytope in three-dimensional space. I will not get into it at all. This is not the point of this talk. The point is that in 2008, Vladimir Pestov have shown, that's from 2008, that at least when gamma is hyperlinear, and I will not yet define what hyperlinear is, it will come at some point in the talk, the answer is yes. The answer is yes, regardless of whether this is 1 or not. Like for genuinely every sum of exponents different than 0. And I'm calling it a motivation because the whole point of talking about Connes embedding problem will relate to this notion of hyperlinearity. This is kind of a way of using hyperlinearity in some interesting context. So let's move now to characters. That will be our gateway into Connes embedding problem. Doron, if I'm not tuning enough.
You're not.
Already. Okay, I'll try to be there. So characters, right? That's the characters. So what I think I just want to define what a character is. If I'm not speaking loud enough, tell me and I'll use like the microphone. But if you hear me, just I'll keep that way. Okay, so what is a character? So if you have a group gamma, throughout my talk, gamma will be some group, so I will not write a group every time. But the function from the group gamma into the complex numbers is a character, and some people in the audience usually call these traces, and character are some subset of these things. If it satisfies three things, okay? So if one, it is, let's call it unital. So it sends the unit of the group to 1 in the complex numbers. The second condition is that it is tracial. So it has the trace property. What is the trace property? The f of xy is equal to f of yx for every x and y. Okay? And the third condition is that it is positive. What does positive mean? That's a bit more like nuance. So for every tuple of elements x1 up to xn, you can construct the following matrix. It will be an n by n matrix. It's f of xi inverse xj for all I and j from 1 to n. That will be an n by n matrix. And being positive means that regardless of which elements you chose, you will get a positive definite matrix. This is positive semi-definite. Okay. So up until now, it's not clear where this definition comes from. Probably people here have many motivations of why to define it, but let's just believe me that this is some interesting definition. Let's define all the collection of all characters of gamma by just char of gamma. Okay. That will be the space of all characters. And notice that you can induce some topology on it, which topology just the pointwise topology as functions. Okay, so like a sequence of functions will converge if for every coordinate converges. So with pointwise topology, this is compact. So this is a nice topological space of all characters. And let's see some examples. And I will not give many examples. I'll give only 2 types of examples. So if you have a unitary representation of gamma, if rho from gamma to ud is a finite dimensional unitary representation, then if you define f to be 1 over d, the trace, so f of x, f of x is 1 over d, the trace of rho of x, then this f is a character. So that's the usual definition that we're used to. Okay, like usually you take the irreducible representations, only then call them characters, but let's just call all of these characters, and I'll even give them, this is a subset of this space, and let's call them the finite dimensional characters. Okay, I'll just denote them by char finite of gamma. And also, I'll use some notation further on. Instead of writing 1 over d trace, I will just write tau. This will be my normalized trace. And again, it's not hard to check that it satisfies all the conditions. That's quite straightforward. now another example. So this will be example 1. Example 2 is that every subgroup, every normal subgroup of gamma induces a character, which character just the characteristic function of n. So just one n of x will be 1 if x is in the normal subgroup and 0 otherwise. Again, okay, clearly it's conjugate invariant, right? And checking positive turns out the characteristic function of any subgroup is positive. Okay, so it's actually nice. And unital 1 is in the normal subgroup, right? So this also follows. Now you want to define what are the hyperlinear characters. So we have a topological space. We have some subset, the finite dimensional characters. I'm just going to close them. So, definition. A character in the pointwise closure of the finite dimensional characters of gamma is called hyperlinear. Gamma hyperlinear, I don't know. Yeah.
Convex combinations of these.
Yeah, probably, right? Like in the finite case, I can work with rational, like if you have rational convex combinations just by the fact that it is, can take direct sum, so I'm not sure that I need convex combinations.
It's the same.
Yeah, because of the rational combination. I have rational combinations for free, yeah. So this, let's call this gamma hyperlinear, and being hyperlinear is being, so, okay, maybe I'll call this just gamma hyperlinear. And a group, let's call it G, which is the quotient of the free product modulo n is hyperlinear. So now I'm defining the notion that appeared here. This is hyperlinear if n, like the characteristic function of n, which is a character of the free group, is free group hyperlinear. And now you can ask the following question, okay? So this is a very general question. Are all characters, let's call them gamma characters, gamma hyperlinear? And the answer is that it depends on gamma. So for some groups gamma, all characters are hyperlinear. For some groups we know that not all gamma characters are hyperlinear. And Connes embedding problem can be phrased, so in my abstract I actually phrase it differently, but it can be phrased as follows. And I'll say that Alain sent me the following reference of Brown from 2006. There's like, he for sure showed it, but I also saw in a paper of Arian Mansour that also it's sometimes reference to Kirchberg already, that knew that these are equivalent ways of Kirchberg, and I'm not sure what is the reference. So they already for sure know that this is like an analog of Connes embedding problem. Are all characters of the free group hyperlinear? So just the case where gamma is a free group over finitely many elements, more than 2, a non-abelian free group. And I will just say that, okay, usually Connes embedding problem is phrased as something about von Neumann algebras. To move from characters to von Neumann algebras is just a GNS representation. So I'm just doing some name dropping, but it's genuinely not a hard, like this equivalence. There are many hard equivalences to the Connes embedding problem. This is one of the easier ones. So it's genuinely like an exercise if you think about it enough. Okay, great. So we have Connes embedding problem. And note that, just a remark, a yes to Connes embedding problem implies that every group, like at least finitely generative group, the way I defined it, is linear, is hyperlinear. Alex always says that this is a bad name because hyperlinear sounds like stronger than linear, but this is actually weaker than linear. But nevertheless, this will imply that every group is hyperlinear, which in particular, you see, will imply the Kerber-Lauerbach conjecture, right? So that's nice. Like if Connes embedding problem was true, we would resolve, for example, this 100 years old problem. But today's talk, we'll talk about the fact that we know now how to refute this problem. Okay, so we know that theorem, Connes embedding problem has a negative solution.
Is it obvious why this implies K and C?
Yeah, because of the theorem that I stated before, that Pestov said that for hyperlinear groups this is just true. So yeah, like Pestov did the work. And actually Pestov uses some like work from the 70s of Gersh, I don't remember, but if you want the references later, like he also uses some classical results from the 70s. Okay, great. So, and this is actually a series of works, but it ended with the Natarajan, Vidick, Wright and Yuen work that I mentioned from 2019. That was the last nail in the coffin.
If the group doesn't have any finite functions, then it will not have unitary representations, and then everything will be empty. Why would it imply the free groups?
Yeah, I don't understand. This is just a question about the free group. It has many finite dimensional.
You say that if it's like a linear, you can't see.
Yeah, I used gamma in two ways. Gamma being let's KLC for G of the form. So every group G, which is a quotient of the free group by some normal subgroup, is hyperlinear. That's what you'll get. And KLC is true for this G, which is a quotient of the free group by this normal subgroup. I just defined being a group being hyperlinear. G is hyperlinear if it's a quotient by some normal subgroup, and the characteristic function of this normal subgroup is a hyperlinear character of the free group, which has many finite dimensional characters. The free group always has many finite dimensional characters, so you can hope to be able to approximate everything using the finite dimensional ones.
This proof from 2008 of the very conjecture was even for groups that
Oh, for every group of this form, so like F modulo n, for n which is a hyperlinear character of the free group. Please ask questions, like I want you to understand, it's a bit technical this part, and maybe I'm not the person to motivate all of this stuff. But please ask questions if it's not clear. I want this to be very well understood.
The question you write are all.
So just
Here I'm asking, okay, you have this collection, characters of the free group. So now gamma is just F. Okay, the free groups, who asked? Can you raise your hand? Yeah, so. Are all characters of the free group hyperlinear? That's the Connes embedding problem. In general, you can ask it for any group, for any gamma, and we know that for some groups it's correct and for some groups it's wrong. Actually, like this study is important when you try to understand, for example, stability of groups and some other properties of groups, but in the amenable case at least. But in general, Connes embedding problem asks just for a specific family of groups, already for the free group with two elements, that's enough, essentially. Just if F is the free group on two elements, is it true that every element in car of the free group on two elements is a pointwise limit point of finite dimensional characters? That's the question. You can phrase it. Yeah.
But to Yane's question, I think maybe it's confusing. So you regard gamma in the Pestov thing about KFC.
That's F mod n.
Gamma is F mod n.
Yeah,
And so hyperlinearity of G of gamma is really a priori your definition is property of the presentation.
Right, but you can show that it's independent of the presentation. Yeah, there are some exercises here. You're right that I chose a specific presentation of G, and it seems as if it's presentation specific, but it turns out that it's not presentation specific. That's an exercise. You're right. I'm glossing over some things. Please, it's not clear from my definition that it is a group property, because maybe G is F mod n, but it's also F prime mod n prime, and n prime is not hyperlinear, and n is hyperlinear. That's a priori it can happen. It turns out that it cannot happen. Check it. exercise.
This equivalent to having an embedding to the power.
You're right, yeah. So
Product of UD.
yes, so usually people define a hyperlinear group as some embeddability property in the ultra power of UDs for these tending to it, like in the metric ultra power of UD when B tends to infinity. Right, but again, I'm intentionally defining it this way for later purposes. More questions or remarks?
Is the question, the answer to the question is yes for linear groups?
I think the answer is no for linear groups. There are groups which are linear, even like right up in upper triangular matrices there is this. What? Right. You're right. That for free groups, right. But even before we knew that the conservative problems are false, there are amenable examples where these are not the same. That's what I meant. And for example, some upper triangular matrices with some properties on the, like, I don't remember the, Alex, what's the name of this group? Okay. Okay, so I hope that at least we understand what is the problem. Let's move on. And the way I'm going to move on is to completely ignore everything that I've done up until now and tell you about quantum mechanics. Now, the way I'm going to do it, I'm going to give you a pseudo-history and pseudo quantum mechanics. So both the history and the actual physics will probably be wrong, but it will be morally correct. Okay? So yes.
Try to take into account this volume.
I think I'll just move it here because I'm not going to, at some point I will need you to remember what happened here. So I'll just cover it with the other two boards and so I want to. And remind me that it's here because I will forget and write it again. Great. So what is our pseudo-history of quantum mechanics? In the end of the 19th century, we learned that there is some particle called an electron. And a few decades afterwards, we learned that these electrons are they don't only have charge, they also have another property called spin. Now, what is this spin? It's just something that makes the electron into a bar magnet with the north part and the south part. Now, Stern and Gerlach devised an experiment in which the following thing happens. So they generated some uneven magnetic field, okay, and in such a way that if you have a bar magnet here and the north is pointing up, when you throw it to the machine it will go up. If you have a bar magnet and the north is pointing down, then it will go down. But if it is in some intermediate orientation, it will go either slightly up or slightly down, and if it's completely flat, it will just move with no effect on it. Okay? So you'll have the whole spectrum of results here according to the orientation of the bar magnet. But once you throw an electron through this thing, okay, so this is what happens with bar magnets. Maybe I'll draw another one, a very bad picture. Once you throw an electron, it never goes in between. It seems as if it is always oriented either completely up or completely down. It will never hit the other side of the Stern-Gerlach apparatus in the middle. Okay? And this is one weird property that people discovered in quantum mechanics. And also, you can do the following. You can kind of concatenate these Stern-Gerlach apparatuses. Okay, like you can first throw it through here, discover that it points up, right? It goes up, and then throw it in a Stern-Gerlach apparatus which is oriented in a different manner. And now you want to ask, okay, what should happen then, right? Like if you expect it, if you first orient it like this, it went up, and now I'll orient it like 90 degrees in the way that a bar magnet should not be affected, it still decides on one side or the other. And it turns out that it decides, so this is called the measurement rule. So if this is the angle of the Stern-Gerlach apparatus, and your bar magnet, okay, so the spin of the electron, but I'm drawing is as if it is a bar magnet. This has angle theta. Then the probability that it will go up is cosine squared of theta over 2. So if it is completely up already, it's with 100% probability will go up. If it is completely down, cosine of pi over 2, right? It's 0, so it will with 100% will go down. But if it's in between, it has some probability of going up and some probability of going down. Great. It turns out that if you have a helium atom and you have 2 electrons, and it's a very cold helium atom, so the 2 electrons are in the lowest energy state inside the helium atom, then by the Pauli's exclusion principle, by Pauli's exclusion principle, they have opposite spins. Now, what does it even mean to have opposite spins? It means that if I have 2 Stern-Gerlach apparatuses and then they are oriented the same, and I throw one of the electrons through one of them, if it went up, the other one, when I throw it, will go down and vice versa. They will always show you the reverse direction of whatever you have. Now, this was very disturbing to Einstein, Podolsky, and Rosen. Okay, so Einstein, Podolsky, and Rosen in 1935 were very disturbed by this, because what can happen is that you can take one of these electrons, put it on Earth, have a Stern-Gerlach apparatus here, and throw one of the electrons here, and you can send one to the moon and have the same scenario, and throw the electron here. And what happens is, once you measure what happened to this one, once you throw it through the Stern-Gerlach apparatus, if it went down, you learn something about the electron on the moon faster than the speed of light allows them to communicate with one another. Okay? So this is called the non-locality of quantum mechanics. Somehow, you learn something about the whole universe instantaneously from doing something in your own part of space. And this seemed very counterintuitive and contradictory to Einstein's theory of relativity. So he was disturbed by this, and their suggestion, Einstein, Podolsky, and Rosen, was that maybe this measurement rule is wrong. Maybe the electron decides beforehand, for every orientation of the Stern-Gerlach apparatus, in which direction it will go. Like, it just decides. This is called the hidden variable theory. So for every direction of space in which the Stern-Gerlach apparatus will be oriented, the electron already decided whether it will go up and down. And they hope that maybe it's consistent with everything, every experiment that we do in quantum mechanics. John Bell came. John Bell. I hope I wrote the name correctly. In the 1960s, and showed that there exists an experiment that distinguishes between the measurement rule and hidden variables. So it took essentially almost 30 years to find a way of saying, yes, quantum mechanics is potentially not consistent with the suggestion of Einstein, Podolsky, and Rosen. And I'll give you the experiment not in the version of John Bell, because it's more complicated, but the version of Clauser, Horn, Holt, and Shimoni. Just a moment, I want to write their name. This is Clauser, Horn, Shimoni, and Holt from 1969. So they refined kind of the Bell experiment. And let me tell you about this formulation. So you can formulate their experiment as follows. You have a referee. That's the person that actually runs the experiment. You should think about this person as the person running the experiment. But in this experiment, there are additional labs. Okay? There is lab A, which is somewhere in space, and there is lab B, which is somewhere in space. Now, what the referee does, it samples two elements, x and y, from F2, just a field with two elements, uniformly. Okay? So it chooses two elements 0, 1 uniformly. It sends x, which is in F2, to lab A, and y to lab B. Now the labs do something. We don't know what is this something, but they can do anything they want. They just need to output back a single bit. They need to output back an element of the field F2. So lab A sends some element A in F2. Lab B sends some element B in F2. And the referee needs to decide, okay, what do I have here? I have four numbers, 4 zeros or ones. I need to tell you, okay, is it a good round of the experiment or a bad round of the experiment? That's the only thing that the referee does. So it will say that the labs won, the labs win, if and only if x times y plus a plus b, okay, this is some equation over the finite field with two elements. If this is equal to 0, the labs win. Okay. That's the whole experiment. So you can run this experiment with some two labs in your actual physical space, and I will say that Clauser, together with Aspect and Zeilinger, won the 2022 Nobel Prize in Physics exactly for like devising these types of experiments and actually implementing these type of experiments in the real world. And I'll tell you what is interesting for us with respect to this experiment.
Just one point, which is that you want the labs to answer so fast that they don't have time to pass information.
You're right. Like here I'm assuming in this specialized case that lab A and lab B can have like some strategy beforehand, but once the experiment starts, they cannot communicate. When you actually try to implement it in physical space, you need to have some rate of answer, like they need to answer fast enough so that speed of light cannot transfer information between them. Okay, so there are like actual physical restrictions on how to implement this experiment in real life, but now I'm just assuming that they don't communicate. Okay, like we're in a perfect scenario where they're not allowed to communicate. But still, if they cannot allow, if they're not allowed to communicate, hidden variables implies that the maximal winning probability of the labs is, okay, it's bounded by 75%, but it's actually equal to 75%. Can someone give me like just how they win 75% of the time for the labs?
Sorry, can I ask, what does hidden variables mean?
So if the electrons, if in our physical space, electrons don't have the measurement rule, for each direction of space they already chose in which way they are going to be measured with respect to Schrödinger apparatus. That's what I mean. That's what's called the classical, like yeah, that essentially our world is governed by classical mechanics. That's essentially what we allow. Yeah. Other questions, remarks? So just people nodded with their heads. Okay, so no one wants to answer directly. If the labs ignore everything and just answer 0, they will win 75% of the time. So, it's not hard to win 75% of the time. You don't need to do anything. You just need to consistently answer 0, and you will win 75% of the time. And it turns out that if the world is governed by classical mechanics, or vice versa, like these electrons behave in the way that I mentioned, that they choose an orientation for like a result for every orientation, you cannot use them to win with higher probability. But the measurement rule, so if the world is actually governed by quantum mechanics, as I described it in its pseudo form before, then the maximum winning probability.
So lab A and lab B, they get each one a copy of one of your.
So I'll explain in a moment how this perfect, best strategy. It's not perfect because it will not win 100% of the time. But the maximum winning probability is cosine squared of pi over 8, which is approximately 85%. So the whole point that it's actually like you have some gap here. That's nice because if you run it in physical space and you see that you do it like millions of times and you consistently pass the 75% using some quantum machinery, then the world is not governed by hidden variables by classical mechanics, but it is still consistent with quantum mechanics, right? That's like why people cared about this whole thing and won Nobel Prizes for this. So let me just tell you, how do you gain this thing? So you generally take a helium atom, you take the 2 electrons from the helium atom, and I'll just give you what is the orientation of the Stern-Gerlach apparatus that they will just throw their electrons through, and what will they answer accordingly. So I will not give you like the calculation why it gives cosine squared of pi over 8. That's essentially just check it with respect to the measurement rule. But what you will have 4 orientations. Maybe I'll use 2 colors. Okay. You will have 4 orientations. 2 orientations with 45 degrees between them for lab A. So this orientation would be if lab A, okay, so this is if x was 1. So it will orient its Stern-Gerlach apparatus this way. This will be if x is equal to 0. And the other one is exactly in the middle here. So this is 22.5 degrees. Okay, and here, I don't know, I'm bad in drawing. This is 45 degrees as well. And this is if y is equal to 0, and this is if y is equal to 1. And the whole point is that up for A implies that A is 0, and I'll write it with the brown. Up for B implies that B, the answer is 1. And you can check that with the measurement rule and the rules that I gave you beforehand. This will actually give you this probability of winning. Okay? So that's nice, and you can actually implement this in physical space. Actually, you can replace the electrons with photons, and then like with their polarity, and then there is a way of doing it very fast. And that's actually how they implement this experiment, not with electrons, but with photons. But the whole point is that generally, you have this now set up. You have this setup when you can ask, given such, so let me call it a computational problem. This is a computational problem, and I will first phrase it computational problem. I will first phrase it non-rigorously, but then I'll give you all the actual definition, because up until now I didn't give you things very rigorous. So the computational problem is given an experiment such as the CHSH1. So I'm going to somehow generalize this setup. You will have a referee, you will have 2 labs, you will send them something, you will get back something, and you need to decide whether they won the round or not, or didn't win this round, okay? So such, given an experiment such as the CHSH1, how well can the labs perform? And what I'm asking actually is if they can have arbitrarily many, finite but arbitrarily many electrons from a helium atom. Okay? So that's essentially the question. And this computational problem is essentially MIT style. Okay? That's essentially MIT style. So now let me formulate it in a more rigorous way. And I hope that, I don't know, the pseudo-history was motivating in some way and not confusing.
Sorry?
Yeah.
So if the labs have access to more electrons, do they do better?
Oh, that's a great question. So the problem that I said that I'm going to reduce to is called Tsirelson's problem. And Tsirilson showed that no. Like even in infinite dimensional kind of resources of entanglement, like this property of always answering differently is some measurement of something called entanglement. So even infinite resources of entanglement don't allow you to win with higher probability in the CHSH experiment. Yeah, that's a very good question. It was open for many years.
Not as a polynomial.
Yeah, so I didn't phrase it as a polynomial question. You're right that once I do it correctly, there will be some running time here, and like essentially there is the running time of the referee here somehow, which which is important for me.
And how essential is it to the way to reducing concept?
So the way I phrase it now, it can be thought of a computational problem and not a complexity problem. It turns out that once you show it with that is as hard as the halting problem, it means that you can just, even in any finite time, you cannot compute it. So it reduces kind of to the computational problem with no restriction on time.
So in order to reduce concept embedding problem, you just need
To refute concept embedding
you
problem?
don't need to put in, not to refute.
I'm just saying that this is kind of a non-rigorous version of MIP star, which is non-rigorous, so it's not good to ask rigorous questions about a non-rigorous differential. But let's move along. So what is this more generalized setup of the CHSH experiments? It's called a non-local game. So definition: a non-local game, is just a tuple consisting of a set X. From now on, another set which is finite, but it will always be just like vectors over F2, like finite vectors over F2. Some distribution mu and some function d. So x and L are just finite natural numbers. Mu is just a probability distribution over x squared. So notice that here, okay, maybe I'll say what are the analogs here in a moment. And d is just a function from x times f2 to the L times f2 to the L to win or lose. So 1 I will think about as win, and 0 I will think about, so it's just a field with two elements, but I interpret 1 as winning and 0 as losing. And let's just see what happens here. So in our case, the set X is F2, okay, in the CHSH situation. I send X's and Y's that come from F2, so this capital X is F2. This L is 1 because the answers are also in F2 to the 1. Okay? The distribution here was uniform over pairs of X and Y's, right? So this probability distribution mu is just the uniform probability on F2 squared. Okay? And this D, you can just calculate D of X, Y, A, B is what we wrote before plus 1. Okay? Because I said that I want to win when this quantity was 0, right? That was my condition. Okay, so at least the previous example falls under this definition of a non-local game. And now I need to tell you how do you formulate all these Stern-Gerlach apparatuses and all this stuff in a more mathematical, straightforward way. So we're very much used to the notion of a probability distribution. So what is a probability distribution for me on a finite set? So A is finite. It's just a collection of non-negative real numbers that sum up to 1, right? That's a finite probability distribution. And a measurement, a d-dimensional measurement, this is usually called a positive operator valued measure in the literature, is a similar function, let's call it M, from again the finite set, which I think of like the set of outcomes. This is a probability distribution. It samples for me an element from A. So measurements are also, they sample to me some element from A. But instead of having outputs which are real numbers, the outputs here are d-dimensional positive semi-definite matrices. Okay? And the sum of the MAs, so again, instead of writing M evaluated at A, I'm just using the subscript because this is common. The sum of MAs is equal to the identity, the d-dimensional identity matrix. Okay? And we will say that this measurement is projective if in addition these MAs are projective. So MA squared is equal to MA for every A. So up until now, this is just some way of generalizing the idea of a probability distribution to matrices. The interesting part comes when you have two of these POVMs. Okay? So given M and N, actually I know that here will be problematic in a moment, so let me move here. So given M and N, okay, they don't need to have the same outcome set. So A from in empty C positive, and N from some other outcome set to the same dimension. That's important for me. So if I have two POVMs, I can measure according to both of them. So you want to sample A and B according to M and N. Okay, and I'm just going to give you a formula for this. The probability that A and B are sampled is equal to the normalized trace, remember the tau from before, over the d-dimensional matrices, of what? Of MA times NB. So there are a few things here that are a bit confusing. Trace of product of matrices can be non-positive, right? A priori. But because MA and NB are positive, convince yourself that this is always positive. And the second thing, this is a probability distribution, so I claim that this actually sums up to 1. So that's another thing you need to check. And this is from the linearity of the trace you get. Okay? So this is actually a probability distribution, and I had this picture of the Stern-Gerlach apparatus. I want to give you another picture here. So the way you should think of it is that you have a new particle, two new particles. These are no longer electrons because they don't have just going up or going down. They have more kind of potential properties that I can measure about them. And they're in something called a maximally entangled state. This is a maximally entangled state.
So P now is a probability measure.
When I write
A
this
times B.
notation, I mean that A and B are sampled, like this distribution that I wrote here is this. The probability that I sample A and B.
So this is notation to say that you take on A times B, this probability measure?
Yeah, yeah. So that's a notation for this probability distribution. And I want to explain what is the physical meaning of this, just for quickly. So you have two particles, and they are in some state which is called the maximally entangled state. And in the case of electrons, this is exactly the state of the electrons in the helium atom. And you throw them through a measuring device. So before we had the Stern-Gerlach apparatus, but this is maybe a more complicated measuring device, which I call M. And I call it M exactly because this POVM is called M. And I have another measuring device, N. And I throw it through here. And this measuring device will tell me something about the electron. This something is just an element from A. And this measuring device will give me some property of the electron, which is just some B in B. And the probability that this measuring device will give me A and this measuring device will give me B when these are maximally entangled is exactly this formula. So there is like a physical meaning of all of this, and the Stern-Gerlach apparatus is the example when the dimension of the matrices is 2. 2 of, yeah.
So when you write MA and B, you actually assume they are commuting.
No. Highly not. This is called the synchronous setup. I will remark about this at some point. I'm not talking actually about the general MIP star, but what's called the synchronous MIP star. But that's enough for Connes embedding problem. That's actually an easier setup to work in. But let me get there, hopefully. Probably not. Let me just define you what is a strategy.
So how are these how is this A related
Maybe,
to X?
yes, I have only 5 minutes, so let me try to get to somewhere where I can at least say this is as hard as the Connes embedding problem, and then we can go and we can discuss later. But a strategy, a d-dimensional strategy for the game G, and I didn't denote it before, but I had this definition of the non-local game, this tuple of X, F2 to the L, blah, blah, blah. I'll just call it G. A d-dimensional strategy for G is a unitary representation, a d-dimensional unitary representation of the free product of F2 to the L X many times. Remember, X was the collection of possible questions. So how is this related to anything that we've done up until now? The answer is the Fourier transform. So notice that when you have a representation of F2 to the L to unitaries, you can take the Fourier transform of it. It's from F2 to the L to non-negative to positive semi-definite matrices, and it's exactly a POVM. Okay, whenever this is a unirep, the Fourier transform is a POVM. Let's just write what's the definition. Rho hat of A is the expectation of -1 to the dot product between A and B of rho of B when I run over all B's in F2 to the L. Okay, so this is the Fourier transform of a unitary representation. And the nice thing is that this is a POVM. And now you should, the way the labs work, so now I need to tell you, why is this a strategy for the game? Like we said that you have like labs and I send them questions like these X elements from X and they answer somehow. The way then they answer is exactly by kind of throwing these particles through measurement devices, and according to the answer of the measurement devices, send me an answer. So the labs, the probability that lab A sends lowercase a and lab B sends lowercase b, given that lab A got x lowercase x and lab B got lowercase y, is equal to the trace, the same thing as we've done before, of rho hat x. And when I denote by rho hat x, I just mean restrict this representation to the x place, right? It's the copy of F2 to the L at the x position. Rho hat x A, rho hat y B. So that's the way the labs actually answer in kind of the quantum setup. And you can define the value in the game using this representation rho as just like you will calculate like it's this, it's let's write it this way. Expectation x and y sampled according to mu, expectation A and B sampled according to rho hat x, rho hat y, right? This is like this distribution of B of x, y, a, b. Remember, this is either a 0 or a 1, so this will be some number between 0 and 1, and that's actually the winning probability of the labs if they use this, unitary representation of the free product of F2 to the L x many times. That's what's the probability that they will win, like in the interaction. Now, let's just say, and I'll stop here, that you can now ask, okay, I ran over all finite dimensional strategies, find the optimum. This will be one number. But if you check, this number depends only on the character of the unitary representation, not on the unitary representation itself. Okay? So I'm actually only calculating things about the character, because the trace is linear, right? So actually, you can ask what is the best, like what is the supremum of this value when you run over all characters of the free group in general. So that's kind of allows you infinite dimensional representations, unitary representations of this thing in tracial for Neumann algebras, actually. But just think about using characters, general characters. And yes to Connes embedding problem implies that the two values agree. Two values agree. So you can check that this thing is continuous, is point-wise continuous with respect to the characters, and thus if the finite dimensional ones are dense, then these two values that I mentioned, optimizing over the finite dimensional or optimizing in general, if you optimize over a dense set, it's the same as the general optimum, right? And this is Tseretelson's problem. Is the optimum over all characters or over the finite dimensional characters of these non-local games are the same? And tomorrow I will elaborate on how to show that there are cases where they are different. Okay? So we will show how do you construct a game G such that the values are. Sorry for being
Yeah, how do you take an expectation with respect to the positive operator value measure?
I told you before that once you have two POVMs, you can do the sampling according to two POVMs. It's even written on the board. A and B sampled according to two POVMs is this thing. I even rewrote it here, and I just said, okay, this expectation is over sampling A and B according to these two POVMs. They are actually projective, so these are projective measurements and not just general measurements. But it doesn't matter. It's just this formula. You see, I said that given two PVMs, I have some formula. The probability that A and B are sampled according to M and N is exactly this trace of M A times NB. That's the, I'm sorry that I wrote it in, like Uri already kind of remarked that this is the definition of this and it's kind of written in backwards. But that's what I've done here, because these are two POVMs. Yes?
The Pearson theorem that we mentioned before basically said that in this simple...
In the CHSH game, you can have an upper bound also somehow, even if you allow infinite characters. Like, so even if you allow all characters of the free group, you cannot get better than this cosine squared of pi over 8. It's a beautiful argument. It's like kind of a beautiful algebraic argument. It shows that.
What about the special characters? The characteristic characters?
Yeah, that's what we don't know. Like we know that Connes embedding problem is false. We know that there are characters which are not dense, like that are not in the closure of the finite dimensional ones, but we don't know that there is any characteristic one, right? One n of someone that would show that there is a non-hyperlinear group. That's a huge question. Do you have any ideas?
There's not a single example of a character which we know is not in the closure.
We know some properties of it, but we don't know how to write a finite description of it yet. Like you can show that there is a game, there is an explicit game for which you know that the optimum with respect to all characters is bigger than the optimum with respect to the finite dimensional ones. That you can show, like this is explicit, but now what is this character that actually goes over and gets a bigger number? We don't know. Yeah, like we don't have the finite explicit description of it.